In the last two videos, we have learned that if two triangles are similar, they have the same shape but are not the same size. We learned that to prove similar triangles, we need to show that corresponding angles are equal or that corresponding sides are in proportion. We only need to prove one of these, but if triangles are similar, the corresponding angles are equal and the corresponding sides are in proportion. And we can use this when considering both angles and the sides of a triangle. Let's look at some examples. Consider the diagram. Part A says, prove that triangle HIJ is similar to triangle LKJ. B, determine the values of M and N. Let's start with part A. Prove that triangle HIJ is similar to triangle LKJ. Now we can consider corresponding angles or corresponding sides, but please remember that in order to use corresponding sides, we need to know the lengths of all three sides of both triangles. In this case, we don't know the length of IJ or the length of KL, so we cannot use corresponding sides, which means that the only way to prove that these triangles are similar is to look at corresponding angles. The first thing we can notice is that HL crosses IK at J. This shows us that angle J1 and angle J2 must be equal because they are vertically opposite angles. So let's mark angle J1 and J2 in red. Now we can make a statement and give a reason. You do not need to write the words statement and reason at the top of your answer. This was just for explanation purposes. Just make sure that you give a reason for every statement that you make. So now we can say angle J1 is equal to angle J2 because these are vertically opposite angles. Let's make our diagram black again and see what else we've been given. The arrows on HI and KL show that HI is parallel to KL. So let's make these sides blue. We know that if we have two parallel lines and a transversal line, then we can look for equal angles. IK cuts both of our parallel lines. So let's make this transversal line purple. Now we've created a Z shape, so we can look for alternative angles. Remember that alternative angles lie between parallel lines, but on opposite sides of the transversal line. Angle K and angle I lie inside the Z shape. So let's mark these angles in green. These are alternative angles, so they must be equal. So we can say angle K is equal to angle I. And now we need to give our reason. They are alternative angles, so we can write alternative angles as our reason. And the reason why these are alternative angles is because HI is parallel to KL. Now let's make our transversal line black again, because this is not our only transversal line. HL also cuts both of our parallel lines. So let's make this line purple. We've now created another Z shape. Angle H and angle L both lie inside the Z shape. So these are also alternative angles. So let's mark these angles in blue. We know that alternative angles are equal. So we can say angle H is equal to angle L because these are alternative angles. We've already said that HI is parallel to KL, so we don't need to write this reason down again. Now we have three pairs of equal angles, but are they corresponding angles? H is the first letter in the triangle HIJ, and L is the first letter in triangle LKJ. So H and L are corresponding angles, and we've just proven that they are equal. I is the second letter in HIJ, and K is the second letter in LKJ. So these are corresponding angles, which we have proven are equal. Finally, J is the third letter in HIJ and in LKJ. J1 lies in triangle HIJ, and its corresponding angle J2 lies in triangle LKJ. And we have proven that these corresponding angles are equal as well. So now we have three pairs of corresponding angles that are equal. So we have proven that triangle HIJ is similar to triangle LKJ because corresponding angles are equal. So we can write AAA as our reason. Now we can move on to part B. Determine the values of M and N. We've just found that triangle HIJ is similar to triangle LKJ. So let's make a note of this up here. This tells us that not only are the corresponding angles equal, but the corresponding sides are in proportion. And we can use this to find the values of M and N. Let's start by writing down the corresponding pairs of sides as fractions. H and I are the first two letters in HIJ. So we can say HI over LK, the first two letters in LKJ, is equal to IJ, the second and third letter in HIJ, over KJ, the second and third letter in LKJ. And we make this equal to HJ, the first and third letter in HIJ, over LJ, the first and third letter in LKJ. Now let's mark these sides on our diagram. Let's start with HI. We can mark this in red. LK is the corresponding side, so we can mark this in red as well. Next, we can mark side IJ in purple and the corresponding side KJ in purple as well. Our third side is HJ, so let's mark this in green, and we can mark the corresponding side LJ in green as well. Now we can fill in the lengths of each side of our fraction. HI is 12 units long, so we can say 12, over LK, which is M. Let's leave it as M for now, is equal to IJ, which is N, we can say N, over KJ, which is 40 units, so we say 40, and we make this equal to HJ, which is 8 units, over JL, which is 20. Now we have two similar triangles, so all three fractions are equal to each other, and we can use this to find the unknown values of M and N. We only need to use two fractions, the fraction with the variable we need to find, and the fraction that has a value in its numerator and denominator. Let's start by finding the value of M. So we're going to use this fraction 12 over M. We can write this over here. Now we need to use the fraction with actual numbers, this one over here. So we can make 12 over M equal to 8 over 20. Now we can see that 8 and 20 are both divisible by 4. So before we start solving for M, let's simplify this fraction. So we're going to have 12 over M is equal to 8 divided by 4 is 2 over 20 divided by 4, which is 5. Now to solve for M, we need to multiply out the denominators of the fraction. So on the left, we're now going to have 12 multiplied by 5 is equal to 2 multiplied by M, which is 2M. To get M by itself, we need to divide both sides by 2. 12 multiplied by 5 gives us 60. So we get 60 over 2, which is equal to M. 60 over 2 is 30. So this is our value for m. Now we can find n. Let's use the fraction n over 40 and the fraction with actual values, 8 over 20. We already know that 8 over 20 can be simplified to 2 over 5. So now I can say n over 40 is equal to 2 over 5. And now we can solve for n. To get n by itself, let's multiply both sides by 40. And we get n is equal to 2 multiplied by 40, which is 80, over 5. 80 divided by 5 is 16, which means that n is equal to 16. Let's do another example. In the sketch, triangle PQR is similar to triangle UTS. PR is equal to 27 units, ST is equal to 16 units, and SU is equal to 12 units. A, calculate the length of QR, and B, prove that PQ is parallel to TU. Let's start with part A. Calculate the length of QR. We have been told that triangle PQR is similar to triangle UTS, which means that not only are their corresponding angles equal, but their corresponding sides are in proportion. And we're going to use this to find the length of QR. Let's start by writing down each pair of corresponding sides as fractions. We have PQ over UT is equal to QR over TS, which is equal to PR over US. Next, let's mark the corresponding sides of our triangles on the diagram. PQ and UT are corresponding sides, so let's mark these sides in red. We don't have the lengths of either of these two sides, so we can't use this to find the length of QR. QR and TS are also corresponding sides, so let's mark these sides in purple. QR is the side we need to find, and TS is 16 units long. Now let's find the third pair of corresponding sides, PR and US, and we can make these sides in the diagram green. PR is 27 units and US is 12 units. So this gives us a fraction with values in the numerator and the denominator. And we can use this fraction to find the length of QR. Let's start with QR over its corresponding side TS, which we know is 16, is equal to side PR, which we know is 27 units, over SU, which is 12 units. Before we move on, let's simplify our fraction 27 over 12. Both of these values are divisible by 3. So we can say QR over 16 is equal to 27 divided by 3, which is 9, over 12 divided by 3, which is 4. Now to get QR by itself, we multiply both sides by 16. So we can say QR is equal to 9 over 4 multiplied by 16. 16 and 4 are both divisible by 4. 4 divided by 4 gives us 1. 16 divided by 4 gives us 4. Now we can see that QR is equal to 9 multiplied by 4, which is 36 units. Now we can move on to part B. Prove that side PQ is parallel to side TU. We know from our work with parallel lines and angle relationships that if we have two parallel lines cut by a transversal line, then we can prove that alternative angles and corresponding angles are equal. We also know that if alternative angles or corresponding angles are equal, then we can use this to prove that two lines are parallel. Here, we need to prove that PQ is parallel to TU. So let's make these lines blue. These two lines are cut by the transversal line QT. So let's make this line green. Now we've drawn a Z shape, so we can consider alternative angles. There are two angles inside the Z shape. Angle Q, let's mark that in red, and angle T2, which we can mark in red as well. If PQ is parallel to TU, then these two angles will be equal because they are alternative angles. So to prove that PQ is parallel to TU, we need to prove that angle Q is equal to angle T2. But we don't know the sizes of any of these angles, so we cannot measure them. But the question tells us that triangle PQR is similar to triangle UTS, which means that all pairs of corresponding angles are equal. So let's use this. Let's mark our diagram in black. P is the first letter in triangle PQR, and U is the first letter in triangle UTS. So P and U are corresponding angles. Let's mark these angles in red. Now we can make the statement that angle P is equal to angle U because these are corresponding angles. And the reason why they are corresponding angles is because triangle PQR is similar to triangle UTS. And we know this because the question has given us this information. So we say given as our reason. Q is the second letter in PQR, and T is the second letter in UTS. So these are corresponding angles as well. Q lies in triangle PQR, so let's mark this in purple. And T is angle T2 that lies in triangle UTS. So let's mark this angle in purple as well. Let's make a statement, and we can say angle Q is equal to angle T2 because these are corresponding angles. But these are the angles we've been trying to find. Let's draw our parallel lines back in blue and our transversal line back in green. We've now proven that these alternative angles are equal. So PQ must be parallel to TU. And we can say PQ is parallel to TU because these are alternative angles. And these angles are equal because angle Q is equal to angle T2. Let's do another example. Explain why triangle ABC is similar to triangle DEC and calculate the values of F and G. In this question, we need to prove that triangle ABC is similar to triangle DEC, and then we need to find the values of F and G. Before we do anything, let's look at the information the question has given us. In triangle ABC, we have these two lines over here and over here. This shows us these sides are equal in length, so they are both 6,1 units long. So we can make the statement that AC is equal to BC, which is equal to 6,1. We know this because the question has given us this information, so we use given as our reason. Let's put 6.1 units on side BC in our diagram as well. In triangle CDE, there's a small line over here on side CD and on side CE, which means that these two sides are both 3.5 units long. So we can make the statement that CD is equal to CE, which is equal to 3.5. We know this because the question has given us this information, so we use given as our reason. Let's put 3,5 units on side CD as well. Now let's look at our angles. In triangle ABC, we know that side AC is equal to side BC. So this is an isosceles triangle. So we can make the statement that triangle ABC is isosceles because side AC is equal to side BC. We know from our work with isosceles triangles that there are two equal sides and there are two equal angles. If side AC is equal to side BC, then angle A is equal to angle B. Let's make a note of this on our diagram, and we can mark angle A and angle B in red. In triangle DEC, we know that CD and CE are both 3.5 units long. So this is also an isosceles triangle. So we can make the statement that triangle DEC is isosceles because side CD is equal to side CE. If side CD is equal to side CE, then angle D must be equal to angle E. Let's make a note of this on our diagram, and we can mark angle D and angle E in green. To prove these two triangles are similar, we cannot use the sides because we don't have the length of side DE. So we have to use corresponding angles. We now know that angle A is equal to angle B, and we know that angle D is equal to angle E, but we don't know their sizes. So let's look at triangle ABC again. In this triangle, angle C is 30 degrees. We also know the sum of the interior angles of a triangle is 180 degrees. So we can say in triangle ABC, 30 degrees plus angle A plus angle B is equal to 180 degrees. Because the interior angles of a triangle add up to 180 degrees. But we already know that angle A is equal to angle B. So this becomes 30 degrees. And now we have angle A plus angle A, which gives us plus and 2 angle A, which is equal to 180 degrees. And now we can solve for A. On the left, we have 2A is equal to, let's move this 30 to the right. 180 minus 30 gives us 150 degrees. If 2A is 150, then A is equal to 150 divided by 2, which is 75 degrees. But remember that angle A is equal to angle B, which means that angle B is also equal to 75 degrees. And now in our diagram, let's take out our red curve at angle A, write in 75 degrees, and we can do the same for angle B. Now we need to find the sizes of the interior angles of triangle DEC. So let's make some space. We can see that lines AE and BD cross at C. So let's mark these in blue. From this, we can see that angle G sits vertically opposite from the 30-degree angle. So we can say angle G is 30 degrees. And the reason why is because these are vertically opposite angles. So let's make our diagram black again. Let's take out G and we can fill in 30 degrees. Now we can use this to find the sizes of angles D and E. So again, we can now say 30 degrees plus angle D plus angle E is equal to 180 degrees. because these are the interior angles of a triangle, we also know that angle D is equal to angle E. So our equation becomes 30 degrees plus angle D plus angle D, which becomes 2 times angle D, is equal to 180 degrees. And again, we can solve for D. 2D is equal to 180 minus 30, which gives us 150 degrees, which means that D is equal to 75 degrees. We know that angle E is equal to angle D, which means that angle E is also equal to 75 degrees. Now in our diagram, let's take out the green curve at angle D, write in 75 degrees, and we can do the same for angle E. Now we have all the interior angles of both triangles, so we can look at corresponding angles. Let's make some space. A is the first letter in ABC, and D is the first letter in DEC. So A and D are corresponding angles. Let's mark these angles in red. Both angle A and angle D are 75 degrees. So we can make a note of this over here. B is the second letter in ABC, and E is the second letter in triangle DEC. So these are also corresponding angles. So let's mark these angles in purple. And we can make a note that angle B is equal to angle E. C is the last letter in both ABC and DEC. So let's mark angle C in triangle ABC in blue and angle C in triangle DEC in blue as well. Both of these angles are 30 degrees, so we can make a note of this as well. Now we can see that angle A is equal to corresponding angle D, angle B is equal to corresponding angle E, and angle C is equal to corresponding angle C as well. So we know that triangle ABC is similar to triangle DEC. We have used corresponding angles to prove this. So as our reason, we write A. We still need to find the value of F, the length of side DE. So let's clear up our diagram. We have just proven that triangle ABC is similar to triangle DEC, which means that corresponding sides are in proportion. So let's write these pairs of sides as fractions. We have side AB over DE, which will be equal to BC over EC, which will be equal to AC over DC. AB is the first side we are considering, so let's mark this in red. DE is the corresponding side, so we can mark this in red as well. Then we have side BC, let's mark this in purple. EC is the corresponding side, so let's mark this in purple as well. Finally, our third side is AC, let's mark it in green, and the corresponding side DC, you can mark in green as well. We need to find the value of F, which lies on side DE. So we need to use the fraction that includes DE and its corresponding side AB. AB is 4,8 units long, so we can say 4,8 over DE does not have a value. So right now, let's just call it F. It's the value we need to find. Now we have values for all of the other sides. So both of the other fractions will have values in the numerator and the denominator. So we can use either fraction. I'm going to use BC over EC. BC is 6,1 units. So we say 6,1 over the length of EC, 3,5. And we can now use this to solve for f. Now, to solve for f, let's multiply out our denominators. On the left, we're going to have 4,8 multiplied by 3,5 is equal to, on the right, 6,1 multiplied by f. To get f by itself, let's divide both sides by 6,1. And we have 4,8 multiplied by 3,5 all over 6,1 is equal to f. Now we can take our calculator. Let's put in a fraction. We can say 4,8 multiplied by 3,5 divided by 6,1 is equal to, let's turn this into decimals, 2,754. Let's round off to 2 decimal places, and we see that f is equal to 2,75. Let's do one more example. In this sketch, WZ is perpendicular to VY and VX is perpendicular to XY. VZ is equal to 12 centimeters, YZ is equal to 14 centimeters, and WZ is equal to 5 centimeters. A. Calculate the length of VW. B. Prove that triangle VWZ is similar to triangle VYX. C. Calculate the length of XY and WX. Let's start with part A. Calculate the length of VW. VW lies on our diagram over here. It is one side of triangle VWZ. Now, the square angle at Z1 is a 90-degree angle. So triangle VWZ is a right angle triangle. So we can make the statement that triangle VWZ is right angled because angle Z1 is 90 degrees. And we know this because this information has been given to us in our diagram. So as our reason, we say given. VW lies directly opposite the 90-degree angle. So VW is the hypotenuse of this triangle. So let's make it red. This means that we can use Pythagoras' theorem to find the length of VW. So we can say VW is equal to one side, let's use VZ squared, plus the other side, WZ squared, all under a square root. Side VZ is 12 units, so we get 12 squared plus side WZ, 5 units, 5 squared, all under a square root. Now we can take a calculator and we can say the square root of 12 squared plus 5 squared is equal to 13. This is the length of VW. Now we can make our diagram black again and make a note that VW is 13 centimeters long. Now we can move on to part B. Prove that triangle VWZ is similar to triangle VYX. We don't know the lengths of all of the sides of our triangles, so we need to use corresponding angles. V is the first letter in VWZ and in VYX, so angle V is the same angle in both triangles. So let's mark it in our diagram in red. Now we can say angle V is equal to angle V because it is common to both triangles. So we use common as our reason. We don't know much about angle W and angle Y, so let's leave it for now and move on to Z and X. Both of these angles are shown in the diagram as square angles, so let's mark them both in green. Z is the last letter in triangle VWZ, and X is the last letter in triangle VYX. So these are corresponding angles. They are also equal because the square angle on the diagram shows us they are both 90 degrees. So we can say angle Z1 is equal to angle X because this information has been given to us. We know from our work on triangles that if we have two pairs of corresponding angles that are equal, then the third pair will be equal as well. This means that angle W1, let's mark it in blue, and its corresponding angle Y, let's mark it in blue as well, will be equal because they are interior angles of these triangles. So as our statement, we say angle W1 is equal to angle Y because these are interior angles of a triangle. Now we have three pairs of corresponding angles that are equal. So now we have proven that triangle VWZ is similar to triangle VYX because all three corresponding angles are equal. Now we can move on to part C1, calculate the length of XY. We have just proven that these two triangles are similar, which means their corresponding sides are in proportion. Let's quickly write down the corresponding pairs of sides as fractions. We have VW over VY is equal to WZ over YX is equal to VZ over Vx. Now let's mark these sides on our diagram. VW is our first side, so let's mark it in red. VY is the corresponding side, so let's mark this in red as well. Then we have WZ, let's mark the side in blue, and its corresponding side YX, so let's mark this in blue as well. The third side of the triangle is VZ, so let's mark this in green, and we can mark the corresponding side VX in green as well. Now we can fill in our known values. VW is 13 units, so we can say 13 over VY, which is 12 centimeters plus 14 centimeters, which gives us 26 centimeters, is equal to WZ, 5 centimeters, over YX. We don't have a value for YX, so let's leave it as YX, is equal to VZ, 12 centimeters, over Vx. We also don't have a length for Vx, so we can simply say Vx. Now we need to find the length of xy, which sits in this fraction over here. And to solve this, we also need a fraction with values in both the numerator and the denominator. So we have to use the fraction 13 over 26. So we can say 13 over 26 is equal to 5 over yx. Now, before we try and solve, we can see that 13 and 26 are both divisible by 13. So let's simplify. 13 divided by 13 is 1, over 26 divided by 13, which is 2. So now we have 1 over 2 is equal to 5 over yx. Now we can multiply out the denominators. 1 multiplied by yx is simply yx, which is equal to 5 multiplied by 2, which means that yx is equal to 10 centimeters. Let's put 10 into our diagram for yx, and now we can move on to part 2. Calculate the length of wx. Wx is this line down here. Now, wx is not a side of an existing triangle, but along with VW, it makes up the side Vx. So to find the length of Wx, we can say Wx is equal to the larger side Vx minus Vw. We already know that Vw is 13 units long, but to find Wx, we first need to find the length of Vx. We already know that triangle VWZ is similar to triangle VYX. We also already know that 3 corresponding sides are all in proportion. We need to find the length of Vx, so we need to use this fraction over here. We know that WZ is 5 centimeters, and we've just found the length of the corresponding side YX is 10 centimeters. So let's use these two fractions. We can say 5 over 10 is equal to the length of VZ, 12, over the length we need to find. Let's call it Vx for now. 5 and 10 are both divisible by 5. So let's simplify the fraction, and we get 1 over 2 is equal to 12 over Vx. Now we multiply out our denominators. 1 multiplied by Vx is simply Vx, which is equal to 12 multiplied by 2. And we see that Vx is equal to 24. This is the length of Vx, but we want the length of Wx. So now we can say Wx is equal to Vx, which we know is 24, minus the length of Vw, 13, and we get an answer of 11 centimeters. And we have now completed this question.